Newton's method uses a series of tangent lines to find the x-intercept. All you're actually doing is finding a tangent line, which you can see here as a black line. Then you're marking the place where that black line hits the x-axis. You're going to go up to your function, where x of 2 hits your function, and then you're going to draw a new tangent line. And you should be able to see that we're getting closer and closer to the actual x-intercept for that function. Well, that's how we do Newton's method graphically. And what we're going to be doing algebraically now is working with the general form of Newton's method. Here we have the basic equation, and we're going to plug in our function, which is cosine of x minus x equals 0. And we want to find the x-intercept for the interval somewhere between 0 and 2. So we're going to take a guess that the actual x-intercept might be 1, because 1 is in the middle of the interval. So let's write the general formula down. The general formula is going to be x plus 1 equals x of n minus our function cosine x minus x all over the derivative of our function. Derivative of cosine x minus x is negative sine x minus 1. Now we want to find x of 1, so using this general form, I'm just going to replace the x's with 1 because that's our guess based on the interval. So we have a 1 there, and a 1 there, a 1 here, and finally we've got a 1 down there. If you evaluate this, x of 1 is going to be 0.75, 0, 3, 6, 3, 8, 6, 7, 9. That's our first approximation. Well, how do we know that's actually the x-intercept? The answer is we don't. So we're going to do a second iteration, x of 2. Only instead of using 1 as our guess, we've got a closer guess now, which is this. So 0.75, 0, 3, 6, 3, 8, 6, 7, 9 minus cosine 0.7503, 6, 3, 8, 6, 7, 9 over negative sine 0.750, 3, 6, 3, 8, 6, 7, 9 minus 1. Now evaluating this for x of 2, we get 0.7391128909. Now you'll notice something interesting has happened here. That is, the first digit for x of 1 and the first digit for x of 2 is the same. So we know that 0.7 is a pretty good approximation to 1 decimal place. But we're not sure about the rest of the decimal places. Now usually 1 decimal place isn't good enough for pretty much anything in physics or engineering. So you want to do more than 1 decimal place. Let's see how many decimal places we can get if we use our new x-intercept. 739.112.8909. And I'll let you fill in the rest of the equation here rather than write out all the numbers. I'll just put x, but you'll want to write in the number And if you evaluate it for x of 3, now we're going to get 0.739 0.851 Now we have 3 digits that are the same, x of 3 and x of 2. So we say we've got the x-intercept to 3 decimal places. Now you could theoretically keep on going on, however many times you want to do the same formula and find the new tangent line approximation is up to what the question asks for and how many decimal places you need. If you need more calculus help, visit calculushowto.com for hundreds of other step-by-step calculus how-tos.